Let's talk about the reaction of a weak acid with a strong base. So these are commonly performed as weak acid titrations. So we might add a strong base like this problem, sodium hydroxide, to a sample of acetic acid with our pH probe in the acetic acid and monitor the pH as we go. And so since we are in acidic solution, our pH curve would start at a low pH and then work its way up and then go through equivalence and have a higher pH. And so we might have an equivalence point at the inflection point of that curve there, and that's where the concentration of base that's been added is going to equal the concentration of our nominal concentration of weak acid at this point, and we would have a volume or moles added for our titrant. And so at that point we are at equivalence at this value. Well, if we go to half that value, at this point the pH is going to equal the pKa according to the Henderson-Hasselbalch equation. And so at this point pH equals pKa, and the concentration of our the concentration of our conjugate base is going to be equal to the concentration of our acid as we've added our strong base to solution. Remember, you're always adding one little bit at a time, so at any point on this curve the hydroxide is consumed up until the point you reach equivalence. Okay, so we'd have our conjugate base and our acid form. We'll look at that in just a moment. So that is the important things we can see on the titration curve. Now, if we are looking at our problem here, I'd like for you guys to go ahead and look at that and try to do it on your own, but we'll go ahead and start working it here. One thing we got to remember, pH is going to be greater than 7 at equivalence. You can read that for yourself. But we're going to have to do a little bit of stoichiometry because we have a strong base. It's going to react to completion before equilibrium develops with our buffer solution that we're forming here. And so because we're forming a buffer solution, we have to first perform the stoichiometry before doing an ICE table, or alternatively we can do the stoichiometry and then use the Henderson-Hasselbalch equation, which we'll do both of those here with this problem. So let's give it a whirl. And remember, we always want to start with our there's my scroll bar. We can start with this problem, and let's see. Start with a balanced equation. This is not dissociation. This is a titration first, so it is a to completion reaction where we are forming our conjugate base and also water as we react the strong base with the weak acid. So at this point we've got to keep track of all our given information. So as we've done in class, we would say, okay, well, our molarities of these solutions are 1 and 2 respectively from the problem, okay, and our volumes are given as well, and so we go ahead and convert to liters since we are moles per liter. 50 milliliters would be 0.0500 to 3 significant figures liters for our volume converted from 50 milliliters. And then from 10 milliliters we'd have 0.0100 to 3 significant figures for our volume. And we do this so we can always get to moles, which is always where we're going with these stoichiometry type problems. So we multiply through moles per liter times liters, and that's going to give us a mole value of 0.0500 moles for acetic acid, and we do the same thing. We're going to get 0.0200 moles of hydroxide. So at this point we are ready to do our change and then final value here for our stoichiometry. So I'll go ahead and put a line through here so we can keep track of everything. And what do we get? Well, our limiting reagent, because we're 1 to 1 to 1 to 1 for everything here, is hydroxide. We're going to consume it first in entirety, and so we're going to lose a portion of our acetic acid. We're going to lose all of our limiting reagent, hydroxide, our titrant here. And so then what do? Well, we're going to create, at this point, that same number of moles of our conjugate base. We don't care about water because it's not going to be used in an equilibrium constant expression. It's the solvent anyway, so there's already more of it hanging around for all of these. Everything's aqueous except for our water, which comes in liquid form here. Now, what's our final moles? Not concentration, 0.03, and then nothing for hydroxide, but then we gain our conjugate base, which is our A- in our acid-base expression. Okay, so at this point, we have a couple options. We're already, we have our moles, but we need molarity for both our calculation of our ICE table or Henderson-Hasselbalch. So we've got to actually figure out what our new volume is. And our new volume, or we could say our final volume, is, well, the 50 milliliters plus the 10 milliliters. So that's going to give us 0.0600 liters for both of these. Oh, we don't care about the zero there, 0.0600 liters. And then, well, that gives us a final molarity of moles per liter, so 0.3 divided by, or 0.03 divided by 0.06 gives us a final molarity for acetic acid of 0.0500 molar. And then our final molarity concentration here for our conjugate base is a third, 0.02 divided by 0.06, repeating, round off to 3 significant figures, and we've got our molarity for the conjugate base. So now we are truly in a buffer situation because we have some of our acetic acid, and our new equation is an equilibrium expression showing our acid-base equation, and we will be forming hydronium because we have both the acid, because we're writing here in terms of pKa, we're given Ka. Have a weak acid, so we use the Ka expression. So the equilibrium constant of this equation is the Ka expression. Okay, so we're in the right place. And now we can use our ICE table. Okay, so if we start with our initial, we just solved it. It's 0.500 molar. For our conjugate base, we're at 0.333 molar. We start with no hydronium. We don't care about water. Our change, then equilibrium, goes like this. We're going to lose some of our acid as it dissociates. We're going to gain some of our conjugate base. We're going to gain our acid. So our equilibrium concentration should look like this. And we can now use the Ka expression, the equilibrium constant, to solve here. And if we plug in, well, we've got a couple of assumptions we can make. Because our equilibrium constant is very small, in fact, pKa, as we look back at the problem there, was 4.74, so that means the Ka is 10 to the minus 4.74, and that's just because pKa is the negative log of Ka, and to get rid of a log expression, it is the power of 10 that gives you whatever, and so we have to account for that using a power of 10. Okay, so that being said, we solve, we get 10 to the negative 4.74. If you like decimal notation, we can go ahead and say that that's, in the calculator, that should be 1.82 times 10 to the minus 5 for your Ka expression. Okay. Well, now, let's talk about these guys here. And then our hydronium right there, we get to plug in everything. Well, it turns out that because our equilibrium constant here, Ka, is very, very small compared to our concentrations, in fact, more than 3 significant figures difference there, we can actually ignore the minus and plus x next to these yellow and green terms here that for HA and A minus. Okay, because they're negligible compared to the accuracy with which we've measured those concentrations. Very, very small because Ka is very, very small. So what we do is we plug in and say, well, now this is A minus 0.333 times x over 0.500. And when we solve for x, by rearranging terms there, we should get 2.73 times 10 to the minus 5 molar for our concentration of H3O plus. If we take the negative log of that, pH is negative log of this number here, 2.73 10 to the minus 5, punch that in the calculator, you should get that pH is 4.56 for our buffer solution. Does that make sense? Well, if pH equals pKa at half equivalence, we're not quite to half equivalence because we don't have quite enough moles or molarity of our A minus to match our acid. Okay, we've got a little bit more acid than we do conjugate base, so that would mean we're slightly less, pH is slightly less than pKa, just by reasoning that out. So we're in good shape. 4.56 is less than 4.74, so it's more acidic than we would be at half equivalence, where pH equals pKa. So we're in pretty good shape there. Now, what are we looking at for Henderson-Hasselbalch? Well, we can only use Henderson-Hasselbalch when we have a buffer solution because we have to have a concentration initial for our conjugate base. We've got to have some acid form here. We've also got to have a number for our base form so that we resist changes in pH in either direction. Otherwise, Henderson-Hasselbalch doesn't apply. But it does when we have that, and with titrations of weak acids with a strong base, it applies. So let's see what it says. Kind of changing gears here. pH is pKa plus the log of A minus over the concentration of HA in molarity. And so if we fill this in, pKa, we said in the problem, was 4.74, and then the log plus the log of our concentration of A minus over our concentration of acid form initial. And we don't have to do an ICE table because we get the exact same answer of 4.56 when we punch that in the calculator for our pH of the solution. We were also asked in the problem, what is the final concentration of acetic acid? Well, just to show you about a buffer, it really doesn't change it that much. So if we have initially 0.500 molar of acetic acid, and we lose an X amount here, well, X was 2.73 times 10 to the minus 5. It essentially leaves, when we subtract that off, the concentration of acid unchanged from its original value. So it was a very small change in concentration that was accomplished by our equilibrium. But however, the hydroxide made a big difference, and so we do get a change. The reaction with hydroxide, the strong acid base, or the strong base reaction with the weak acid, lowered our concentration from 1 to 0.5 molar. So we should say the final for our concentration of acid form is 0.500 molar, because when we subtract off the X from equilibrium forming, we get very little change because it's so small compared to our value here. We started with 1 molar, but then we did a weak acid strong base reaction that got us to 0.500 molar. So we've answered all the questions we were asked. pH of the solution, 2 different ways we did it. Either way you like is fine. You can do it either way. And then our concentration of acetic acid final was 0.5.